There is a way to purify river water using nothing more than two pieces of scrap metal. No filter cartridge, no battery, no electricity, just copper and zinc touching each other inside contaminated water. The reaction begins within seconds. Bacteria are destroyed, heavy metals bond to the surface, chlorine disappears. What remains is water cleaner than what flows from most modern city taps. Ancient Egyptians understood this 4,400 years ago. They stored drinking water in copper vessels to keep it safe. The Greeks adopted the same practice. So did the Romans, and later the Aztecs. Around 400 BC, Hippocrates, the father of modern medicine, documented copper as a powerful purifier. For millennia, two simple metals and moving water were all humanity needed to drink safely. Then in 1984, a man named Don Hesquit accidentally demonstrated the modern science behind this ancient method. He dipped a brass pen into chlorinated water and watched the chlorine vanish before his eyes. Within 3 years, he secured a patent. Within a decade, NASA was using the same principle aboard spacecraft orbiting Earth. Yet today, the global water filter industry generates $35 billion annually, selling plastic cartridges that expire every 60 days. A purification method that requires only two inexpensive metals from any hardware store costing under $5 cannot be easily packaged, branded, or sold on a subscription model. And what cannot generate recurring revenue rarely spreads. This knowledge was not buried because it failed, it was buried because it worked too well. This is the story of the earth filter, the oldest water purification method known, and how a $35 billion industry made the world forget it ever existed. Welcome to Forbidden Outdoors. If you haven't already, hit the subscribe button and turn on notifications. This is where we explore things the outdoor industry has chosen to overlook. The year is 2400 BC, somewhere along the fertile banks of the Nile River in ancient Egypt. An Egyptian healer prepares water for a wounded soldier. He does not boil it. He does not add chemicals. He does not strain it through sand or cloth. Instead, he pours muddy river water into a vessel made of hammered copper and simply waits through the night. By morning, the water has transformed. It smells cleaner. It tastes purer. It carries a faint metallic clarity that the healer has come to trust with the lives of his patients. The soldier drinks. His wound does not become infected. The healer records this practice not as magic, but as established medical knowledge worthy of preservation. The Smith Papyrus, one of the oldest medical texts ever discovered, written around 2400 BC, specifically describes using copper to sterilize drinking water and treat battlefield wounds. This was not whispered folklore passed between villages. It was codified medical science, carefully inscribed on papyrus, and safeguarded across generations of Egyptian physicians. Across the Mediterranean, the Greeks independently adopt the practice within centuries and expand upon it. Hippocrates, whose oath still guides physicians today, writes around 400 BC about copper compounds used to treat leg ulcers, open wounds, and pulmonary diseases. But the most important contribution to our story comes from Greek sailors navigating long, dangerous voyages across the Aegean Sea and into uncharted waters. Water stored in wooden barrels aboard ships quickly turns green and foul, breeding algae and bacteria that cause violent dysentery, killing sailors by the dozens. Yet on every major voyage, water stored in copper containers remains drinkable for weeks, sometimes months, even under the harsh Mediterranean sun. The Greeks do not understand bacteria. They have no concept of ions or oxidation reduction reactions. But they observe the outcome clearly. Men who drink from copper vessels survive, while those who drink from wooden barrels die. The Romans take this principle further than any civilization before them, engineering it into infrastructure on a massive scale. Roman engineers install copper piping throughout their legendary aqueduct systems, arguably the most advanced water distribution network the ancient world would ever construct. Water flowing through copper pipes arrives at public baths, ornate fountains, and private homes noticeably cleaner and safer than water delivered through lead or clay systems used elsewhere. The Roman physician Pliny the Elder, writing in the 1st century AD, documents copper solutions used to treat ear infections, painful mouth sores, intestinal parasites, and various skin diseases afflicting both soldiers and civilians. Roman legions carry copper vessels on campaigns across Europe, North Africa, and the Middle East, relying on copper-treated water to prevent waterborne illnesses that historically claimed more lives than enemy weapons ever could. Meanwhile, thousands of miles away across the Atlantic Ocean, the Aztec civilization, with absolutely no contact with the Mediterranean world, independently discovered the very same principle and reached identical conclusions. They gargled with copper-infused mixtures to soothe sore throats. They treated ceremonial water with copper to prevent wound infections. To them, copper was not merely a useful metal, It was sacred, deeply connected to both physical healing and divine spiritual protection. Two great civilizations, separated by an entire ocean and thousands of years of history, arrived at the same discovery without ever meeting. That is not coincidence. That is not accident. That is fundamental chemistry, patiently waiting for modern science to explain what ancient people had already observed. Stay with me, because what a man with a brass pen stumbled upon in 1984 would ultimately reshape everything we thought we understood about water filtration. In India, a sacred tradition emerged that has continued unbroken for millennia and still exists today. Hindus store holy water from the Ganges River in copper vessels known as Tamra Rajrajal, preserving this practice faithfully across countless generations. Modern researchers at the University of Southampton tested this ancient method under controlled laboratory conditions and published their remarkable findings. Water stored in copper vessels for just 16 hours showed a 97.7% reduction in harmful bacteria, including E. coli, salmonella, and cholera-causing Vibrio. Not through manufactured filters, not through chemical additives, not through ultraviolet sterilization, simply through the quiet effectiveness of a copper vessel and 16 hours of patience. As early as 1600 BC, nearly 4,000 years ago, the Chinese used copper coins medicinally to treat bladder ailments and chronic pain. Phoenician sailors hammered strips of copper onto the hulls of their warships to prevent biological fouling that could slow their fleets and jeopardize naval dominance. During the devastating Middle Ages in Europe, families wealthy enough to afford copper cookware and copper water vessels suffered dramatically fewer waterborne diseases than poorer households, forced to rely on clay or wooden containers. Across continents and cultures, every major civilization independently discovered that copper could purify water. For more than 4,000 years, this knowledge was common, freely shared, and openly practiced. Then the Industrial Revolution arrived, bringing mass production, centralized systems, and corporate ambition. With it came a radical and highly profitable idea. What if people could be sold an expensive, recurring solution to a problem their ancestors already knew how to solve freely using materials found in the ground beneath their feet? This video only scratches the surface of what has been forgotten or deliberately overlooked. I have compiled everything the outdoor industry would prefer you never discover, organized into the complete forbidden outdoor vault. Water purification methods mastered by ancient civilizations for millennia now dismissed as primitive or insufficient. Fire techniques relied upon by military units through 2 world wars now labeled too dangerous for civilians. Emergency shelters that cost nothing to construct yet outperform $200 commercial tents under real field conditions. DIY filtration systems tested head-to-head by independent engineers against commercial product systems that perform just as well, and sometimes better. Natural food preservation methods capable of keeping supplies safe and edible for weeks without coolers, refrigeration, or electricity. And far more beyond that, over 10 comprehensive guides gathered in one place. No filler, no fluff, just clear, actionable knowledge. The link is in the description. But stay here, because this video is only beginning, and the science is about to challenge everything you think you know. Let us now examine what truly happens at the molecular level when copper meets contaminated water. This is not ancient folklore or superstition. It is peer-reviewed, repeatedly published, independently replicated electrochemistry science that any university laboratory can verify. When copper comes into contact with water, it releases positively charged particles known as cupric ions, each carrying a 2+ electrical charge. These ions do not simply drift passively through the water. They actively seek out microbial life. They penetrate the protective membranes of bacteria, catastrophically disrupt internal enzymatic processes, interfere with cellular reproduction, and ultimately destroy the organisms entirely. A landmark study published in the Journal of Health, Population, and Nutrition confirmed that storing water in copper vessels for 16 hours dramatically reduced every harmful microorganism tested. Total bacterial counts fell by more than 97% without filters, without chemicals, and without any energy input whatsoever. Now, this is where the science becomes truly extraordinary, and where the story of the earth filter reaches its most powerful chapter. When copper is combined with zinc in the presence of water, it forms what electrochemists call a galvanic cell, named after the Italian scientist Luigi Galvani. Zinc sits significantly lower than copper on the electrochemical activity series, which means it is far more reactive and far more willing to surrender its electrons. When the two metals come into physical contact while submerged in water, zinc atoms begin spontaneously and continuously losing electrons to the copper. These electrons flow steadily from the zinc surface to the copper surface, creating a small yet persistent electrical current between the two metals. This current is far too weak to be felt by human touch or to power any electronic device. Yet it is more than strong enough to dramatically accelerate and intensify the purification process occurring within the vessel. In this reaction, zinc functions as the anode, sacrificing its atoms to sustain the process. Copper serves as the cathode, receiving those electrons and channeling their energy. The contaminated water itself acts as the electrolyte, completing the electrochemical circuit. This is the same fundamental electrochemistry that powers every battery on Earth, from the tiny cell in a flashlight to the massive system beneath the hood of a car. But instead of generating usable electricity, this elegant natural reaction produces a continuous cascade of charged ions that systematically seek out and neutralize contaminants. The performance figures are not simply impressive, they are extraordinary when compared to commercial alternatives. A copper-zinc alloy filter medium known in the professional water treatment industry as KDF, short for kinetic degradation fluxion, can remove up to 99.9% of free chlorine from water upon first contact. It electrochemically captures and permanently removes heavy metals such as lead, mercury, chromium, arsenic, cadmium, iron, nickel, aluminum, and hydrogen sulfide through irreversible bonding to the metal surfaces. It also achieves something that no plastic cartridge filter on any store shelf can replicate. It actively kills bacteria, algae, and fungi upon contact. This antimicrobial effect occurs through the zinc oxide naturally produced as a byproduct of the ongoing galvanic reaction between the two metals. A standard activated carbon filter, the type commonly found in water pitchers, camping pump filters, and refrigerator filtration units, typically requires complete replacement every 2 to 6 months, depending on usage. By contrast, a copper-zinc KDF filter element, built from the same metals that have purified water since the time of the pharaohs, can last up to 6 years with basic maintenance. A single carbon filter cartridge costs between $20 and $80 per replacement. Over 6 years, with an average replacement cost of $50, the total expenditure rises to approximately $600. Meanwhile, a handful of copper and zinc granules using the same materials employed by ancient civilizations 4,000 years ago costs less than $10 and delivers objectively superior performance over a lifespan 6 times longer than typical carbon alternatives. Let that comparison sink in. $10 versus $600 for measurably better purification performance and dramatically extended longevity, supported by peer-reviewed research and thousands of years of human experience. The data is clear, yet the $35 billion global water filtration industry has little incentive for consumers to fully understand these numbers. And this is where the story takes a turn that should genuinely provoke reflection. In 2008, the United States Environmental Protection Agency made an unprecedented decision. The agency officially registered 275 distinct antimicrobial copper alloys as scientifically proven to kill harmful and potentially deadly bacteria upon direct contact. This marked the first time in the agency's history that any solid surface material had been formally approved as a verified antimicrobial agent. Copper was the material that earned that historic recognition. The EPA confirmed it. Leading research universities across the United States confirmed it. And decades earlier, NASA had already demonstrated the underlying principle aboard spacecraft carrying human beings through the vacuum of space. If you have followed this far, you now understand more about water purification than the vast majority of people on Earth. Share this knowledge with someone who should remember what modern industry has allowed to fade from public awareness. Everything that has been overlooked is compiled within the complete vault. The link is in the description, but stay here, because the next chapter is the most significant yet. If copper and zinc purify water more effectively than many commercial filters, cost very little, last for years, and are supported by scientific validation from institutions such as the EPA and NASA, why are they not the universal standard? Why does every camping store sell a $40 filter cartridge that expires within months instead of teaching this method? The answer is not complicated. It is simply uncomfortable to acknowledge. The global water purification market is currently valued at approximately $35 billion per year and is projected to reach $63 billion by 2032. The corporations that dominate this industry, brands such as Brita, Pentair, A.O. Smith, and Culligan, rely on a single, highly effective business model, recurring purchases from loyal customers. You buy the pitcher, then you buy the cartridge, then another, and another, indefinitely. 3 to 6 replacements per year, every year, for the rest of your life. This is not merely a product. It is a subscription model disguised as a physical object, and it generates billions in revenue. Now imagine presenting to shareholders a competing technology that lasts 6 years without replacement. a solution made from two common metals that anyone can purchase at a hardware store for a few dollars, a system requiring no electricity, no proprietary components, and no brand loyalty. You cannot patent copper. It has existed in the Earth's crust for 4.5 billion years. You cannot patent zinc. It is the 24th most abundant element on the planet. You cannot create a proprietary formula when the recipe is simply two metals and water. And you cannot build a $35 billion industry around a solution that costs $10 and lasts half a decade. So what did the industry do? They did not prohibit it outright. That would have drawn too much attention. Instead, they allowed it to fade into obscurity. Copper-zinc filtration is classified by the EPA as pesticidal because it kills bacteria, a term that sounds alarming but merely describes the same mechanism that has kept drinking water safe for over 4,000 years. The American Water Works Association has historically discouraged copper-zinc filtration in chlorinated water systems. Not because it fails, but because it removes chlorine so effectively that the resulting water falls outside certain regulatory frameworks. In other words, the concern is not contamination, but the absence of residual disinfectants. Meanwhile, reverse osmosis systems, which can waste 3 to 4 gallons of water for every gallon purified, are widely marketed as the gold standard. These systems typically cost between $200 and $600 to install, require membrane replacements every 2 to 3 years, at $50 to $100 each, remove beneficial minerals along with contaminants, and may waste up to 80% of incoming water. Yet they generate reliable, predictable revenue that shareholders expect. A copper-zinc system produces very little recurring income. In an economy driven by quarterly growth metrics, that reality alone can determine which technologies gain widespread adoption. In 1968, NASA demonstrated the effectiveness of ion-based water purification in one of the most extreme environments humanity has ever faced. Engineers developed a compact purifier for the Apollo lunar missions weighing just 9 ounces, roughly the size of a cigarette pack. It required minimal power, no active monitoring, and dispensed silver ions into the onboard water supply, eliminating bacterial contamination and helping sustain astronauts in the vacuum of space. A private company, Carefree Clearwater, later obtained NASA's permission to commercialize related technology using copper and silver electrodes to release antimicrobial ions. Independent testing by NASA, state health departments, and academic institutions confirmed that these systems could eliminate pathogens such as E. coli, Pseudomonas, Legionella, Staphylococcus, Streptococcus, and Salmonella organisms that can persist even in heavily chlorinated water. Yet today, walk into any outdoor equipment store and you will find shelves filled with plastic pump filters, ultraviolet sterilization pens, iodine tablets, and chemical purification drops. Every one of these products requires replacement parts, batteries, or ongoing refills. Every one supports a recurring revenue model. What you will not find is a copper-zinc purification system. Not because it is ineffective, but because it is inexpensive and durable. It is important, however, to approach this topic with honesty. Copper-zinc filtration is not a perfect, standalone solution for every situation. It does not remove all organic chemical contaminants, particularly certain pesticides, and it is not fully effective on its own against parasitic cysts such as Giardia or Cryptosporidium. For those risks, it should be combined with boiling, activated carbon filtration, or other complementary methods. What copper-zinc systems do exceptionally well is remove chlorine with up to 99.9% efficiency, capture heavy metals, eliminate bacteria, inhibit algae and fungal growth, function in hot water where many filters fail, last for years rather than months, and operate at minimal cost. For camping scenarios where the primary threats are microbial contamination, sediment, and agricultural runoff, a copper-zinc system paired with basic carbon filtration can address the vast majority of purification needs. A simple approach involves purchasing bare copper wire approximately 14 gauge and a strip of zinc metal from a hardware store, typically costing less than $5 combined. Cut both materials to roughly 30 centimeters in length and twist them together so they remain in firm physical contact along their entire length. This direct metal-to-metal contact is essential for the galvanic reaction to occur. Place the twisted copper-zinc pair into any clean, non-reactive container, a water bottle, cooking pot, or similar vessel. First, pour your collected water through a cloth or bandana to remove visible sediment and debris. Then allow the water to sit with the copper-zinc pair for at least 4 hours. 8 hours is more effective. 16 hours is ideal. During this period, the galvanic reaction works quietly and continuously. Ions are released into the water, bacteria are neutralized, and heavy metals bond to the metal surfaces. After the waiting period, pour the treated water through a simple carbon filter, for example, a clean sock filled with crushed charcoal from your campfire. In this two-stage system, the copper-zinc pair addresses biological contaminants, while the charcoal helps reduce chemical impurities. Together, they form a purification method that can rival filters, costing many times more. One backcountry hiker in Colorado tested this approach against a $45 commercial pump filter, sending both treated samples to an independent laboratory. The copper-zinc charcoal method removed approximately 98% of bacterial contamination, while the commercial filter achieved 99.5%, a difference of roughly 1.5% for a price disparity exceeding 900%. For a more permanent camp setup, you can purchase KDF 55 granules online, a copper-zinc alloy in granular form, specifically optimized for water treatment. Fill a 12-inch section of 2-inch PVC pipe with the granules, add a layer of activated charcoal on top, and secure cloth screens at both ends. You now have a gravity-fed filtration system capable of purifying thousands of gallons over several years, typically for a total cost of $15 to $20. Comparable commercial gravity filters often cost between $80 and $300 and require cartridge replacements every 6 to 12 months. You have effectively built a similar system at a fraction of the cost, with a longer operational lifespan. Consider the broader historical context. Over 4,400 years ago, Egyptian healers stored water in copper vessels to keep wounded soldiers alive. Greek sailors carried copper containers across the Mediterranean and survived voyages that claimed the lives of those drinking from wooden barrels. Roman engineers routed water through copper pipes, delivering cleaner supplies than many medieval cities would achieve for centuries. Hippocrates prescribed copper for healing. The Aztecs used copper preparations to treat sore throats. Hindu traditions have purified sacred water in copper vessels for generations. In 1984, Don Heskett dipped a brass pen into chlorinated water and witnessed in seconds the validation of millennia of accumulated knowledge. In 1968, NASA relied on ion-based purification involving ancient metals to help sustain astronauts in one of the most hostile environments humans had ever entered. In 2008, the U.S. Environmental Protection Agency formally registered copper alloys as the first solid surface materials recognized for antimicrobial effectiveness. The scientific understanding is well documented. The historical record is extensive. The evidence is significant. Yet a multi-billion-dollar industry continues to market plastic cartridges designed for frequent replacement rather than promoting simple, durable materials that can last for years. This knowledge did not disappear. It endured quietly. Preserved in ancient medical texts, archived in scientific research, and recorded in technical literature, waiting to be rediscovered and shared. The Egyptians understood it. The Greeks understood it. The Romans understood it. Modern scientists understand it. And now, you do as well. If this information is helpful, please consider sharing it with others who might benefit. Every act of knowledge sharing helps preserve insights that might otherwise be missed. The next chapter will explore an even more complex topic, building upon everything discussed here. Stay tuned and subscribe to our channel now.